Um, yeah, so this presentation is about RamaLama, which is basically a tool that makes AI workloads on ARM boring or easy to run and use. I'm Eric and I work for Red Hat. I have a varied background, I guess, in regards to AI. I created this tool, and I'm also an upstream llama.cpp maintainer. And this is my partner Sergio, who's doing the talk with me. Sergio is the best virtualization guru I know. Created and maintained libkrun and also contributes to llama.cpp in various projects around the place. I'm having a bad day. The clicker doesn't work. So yeah, I'm going to try and get through the slides really quickly because it's only half an hour talking. There's a lot of slides. I actually made some last minute edits to the slides, but I'm at an issue with the HDMI on my MacBook Pro. This is a slightly older version of the slides, but we'll make do. I also can't do the demo because I wanted to demo it on an ARM machine. And anyway, we'll see how we go, and maybe I can show a demo on the end, and the streamers won't be able to see it. So RamaLama is all about an easy and secure and open way to run and serve LLMs locally. So I don't know how many of you have played around with LLMs on like real hardware, but if you've ever experimented with an LLM or run one locally or build an AI powered application, it's not so simple. These are huge complex stacks, and it's even exaggerated on ARM because on ARM there's such an array of different like NPU, GPUs, and other accelerators you can use that setting up an AI stack is kind of hard. So this helps to make that a bit easier. So yeah, these are some of our goals, just to make run and serving a chatbot, not just chatbot, any AI workload with a single command to secure it within containers, so you encapsulate your workload and you can have more trust and control about what's actually running on your system without it running insecure, and God knows what can happen. Yeah, and we build using open standards and AI building blocks. So here's an example you can run. In this case, it's Gemma, but you can run any model you want. This is RamaLama run Gemma, and if you run this, you get a little chatbot CLI on your terminal, and you can query the LLM as you wish. So yeah, we're very containers focused in this project in a couple of ways. So when you run that last command, I showed, there's a couple of things that happens there. So first thing it does, it inspects your hardware, and it kind of tries to figure out what's the primary accelerator and what language does that accelerator talk. So is it CUDA, is it Vulkan, is it, what are some other ones? There's one called CAN, Musa, but it'll try and identify what your primary accelerator likes to speak, pull down the inferencing runtime in a container image for RamaLama to use, and then it'll attempt to pull your model if it's not pulled down already. So if it's Gemma 3, it'll pull it from some model registry. That could also be a container registry, or it could be Hugging Face, or it could be the ollama registry, because we support multiple model registries to pull from. Yeah, and that could get you running your container locally. And then we also have other functionality if you kind of want to push your models to a container registry to distribute them around the network. We offer functionality to do that also. And I'll go through that again in later slides. So yeah, these are just some features we added to make things easier. So we allow short names. If you've ever pulled a model from like a place like Hugging Face, it's this like big long string basically. But basically, we have short names files, which are config files, and they basically say, if I specify gemma3, pull from this Hugging Face location. So we maintain some short names files, but you can also create your own. It's just a configuration file in your system. We also resolve some of these short names on the ollama registry. So that's kind of the same concept. If there's not a client-side short name, you query the ollama model registry, and you're like, oh, this short name is this model, and you pull down that model. And this is just a feature I stated before on the right. We try and make running models with optimal performance on your system easy. So we'll try and pick the best inferencing runtime for your environment, pull that container, set up the container for you, poke the relevant holes in the containers to talk to the accelerator properly, and that's all done under the hood. And you might even be a bit opinionated about the inferencing runtime you want to use. So say say RamaLama decides, oh, we're going to automatically pull down CUDA because we detect Juva. NVIDIA GPU somewhere, you might say, well, I want to use Vulkan because I want to use the open source implementation. It's a smaller container image. I want to use an open source implementation. You can select, I want to use Vulkan as an alternative to CUDA. So it's very flexible that way. Yeah, this is just describing the general advantages of containers. If you've ever run an AI workload on your system, like by design, they're not very deterministic processes. They can be quite creative, and they can also run away with resources on your system if you're not so careful. So containers helps control and isolate your workload, and you can even do things like turn off external network if you're worried the AI workload might reach out on the network, and do things that you're not comfortable with, and you want to restrict the workload a little more. Yeah, so RamaLama is all about maximizing choice. I spoke about this already. It allows you to pull from multiple model registries. Some examples here are ollama. Another one is Hugging Face, or you can pull from OCI container registries. We had a contributor only last week. He's based in China, and in China they have this model registry they like to use called Model Scope. And I think from the commit messages, what I gathered is they're actually firewalled off from Hugging Face. So it's like, can I add support for Model Scope? And I was like, go ahead. And so we now support that as well. So that's what we're trying to do. RamaLama is all about choice for the inferencing runtimes. Although, because we are very container focused, we do recommend you push and pull from OCI registries. That's kind of our recommended approach, because you're pushing and pulling container inferencing runtime, so you're going to need that piece of infrastructure anyway. So it does simplify your deployment if you just use OCI registry to push and pull models. Also, it's just more consolidated and simpler. You don't have to mess around with firewall rules. So that's kind of the approach we recommend. This is similar to RamaLama Run, but instead it's RamaLama Serve. What the RamaLama Serve command does, it's very similar, but instead of just giving you a chatbot, it gives you an open AI compatible server endpoint, and then you can connect various AI tools to do chatbots or coding tools. Or I was playing around with something recently, vision models, which is quite cool. You can get the model to process images rather than text. We're also integrating something called LlamaStack. LlamaStack is this new project from Meta. This is something, I'm actually not an expert on that, so some other people on the RamaLama team are, but it's connecting the front and the back ends together. In my head, I kind of think of it like Kubernetes for AI, but it's this cool new project from Meta we started integrating. Here's some other features of RamaLama. So once you kind of get your workload working locally on, say, a MacBook Pro or whatever, you might be like, well, how do I kind of get this running on some on a server or in some data center? So we provide these generators, so you can generate a quadlet. If you haven't encountered quadlet before, quadlet's kind of like it's a system D generator, so it'll generate a little unit file which you can start and stop your container like a system D service essentially. And we also have Kubernetes generators if you want to run these workloads on Kubernetes. Here's some various open source projects we worked with. Obviously, it's all fully open source. It's all upstream. So, Granite by IBM, D3 projects, llama.cpp. These are all by this company called ggml.org. So we do quite a bit of work with them. And the Universal Blue guys, we also collaborate with them quite a bit, because Universal Blue is an immutable operating system. It's a container-focused operating system, so they kind of like how we're trying to do things in a cloud-native way. Yeah, and here's an example of a collaboration we did recently for KubeCon. Basically, what happened here is, as I said earlier, Universal Blue are a fan of our approach, and so are Ampere. Because Ampere were playing around with RamaLama, and they're like, this actually runs really well in our hardware. So at KubeCon, this is just a demo they were doing. This is basically RamaLama running on an Ampere machine, which is a really interesting workload, because in this case it wasn't accelerator-based inferencing at all. It was CPU-based inferencing. But Ampere machines have so many cores, like 128, that this workload is kind of interesting when you start bumping the threads up.
192. Sorry.
192. Yeah, sorry. Once it goes above 100, I start to lose count. But these are some various hardware we ran on, and inferencing backend. So like we have people running an Apple Silicon, Ampere, Huawei. There's been others, but these are just some in the back of my head. And we also build for like CUDA on ARM, Vulkan on ARM, Can on ARM. There's a guy in a PR I reviewed literally an hour ago that's integrating this other backend called Musa, which is by a company called More Threads. But yeah, we're adding support for all kinds of protocols and ARM hardware all the time. This is just why ARM for AI in general. These are some of the reasons I think ARM is well suited for AI. So we're getting to the point with AI workloads where power is becoming the limiting factor, and ARM hardware is quite power efficient, so that's a win there. Obviously, you can offload your AI workload onto an external GPU, but if you're using the SoC itself, there's multiple components that can be suitable for inferencing, be it a GPU, an NPU, CPU, or other accelerators. It's very scalable architecture in many different ways, from IoT to edge to cloud. We just spoke about an Ampere machine with 192 cores, so yeah. The other thing, and I think this is going to be big, edge AI brings lower latency AI responses. You know, there's a lot of talk about building up these huge data center with like 1 million NVIDIA GPUs, and yeah, that will give you great throughput. But I think we're going to get to the point where people are going to, want to lower the latencies between request and responses on their AI workloads. I think edge AI is going to be quite big, and I think ARM has a big place to play in the edge AI space. You can get high memory bandwidth, and I use the Apple marketing term here, but using unified memory and not having the copy between RAM and VRAM, that can be kind of useful as well. So ARM is pretty neat for that. Why RamaLama for ARM? If you played around with various AI frameworks, you'll notice a lot of the time the focus is kind of like on NVIDIA GPUs and x86, and they're kind of like after that, we don't really care so much, it's not a priority. And when they do support ARM, it's typically for Mac OS, not Linux, and that's just kind of for like developers on their MacBooks or whatever. But in RamaLama, we're different. We already went through it, but you know, if you want to work with us and open PRs and help us test, we're open to running on basically pretty much any piece of ARM hardware. And this is good, it avoids lock into a specific piece of hardware. You'll notice on most of the AI tools out there, they're either trying to lock you into a very specific piece of hardware or a very specific piece of software or model registry or something like that. So we try to be agnostic to all that. Cloud native approaches, I wouldn't say this is specific to ARM. I actually deleted this on the latest version of my slides, but anyway, it's a nice quality of RamaLama. And I'll hand you over to Sergio. Sergio's going to talk about Vulkan.
Thank you very much.
Areas.
So, hello everyone. As Eric said before, RamaLama detects which is your primary accelerator and tries to pull the best setup for the best framework for that accelerator. But that means that we had to support a large number of images and a large number of stacks, which it's a lot of work, frankly, and we can expect it to be optimize all of them at the same level. This is the reason why we are mainly focusing on Vulkan. We think that GLSL, the GLSL language, is expressive enough to support and provide good performance with most inferencing use cases. Over the last year, we've seen a lot of advance on the on projects like llama.cpp, on the Vulkan backend of llama.cpp, to the point in which the Vulkan backend is reaching near the same performance as the CUDA backend for NVIDIA GPUs, and roughly the same performance for the AMD GPUs equal to the ROCm framework. So this is giving less and less of a reason to have different frameworks, different stacks for each one of those GPUs. And that simplifies the cost and also makes testing easier, makes creating the tools easier, makes everything easier for us, which allows us to focus on the really important stuff and not just on the stack. Another really good advantage of this is that we can rely exclusively on a fully open source stack that is widely available and is driven through Mesa. Another interesting aspect we would like to talk is that, as Eric said, we want RamaLama to always use containers, even on macOS. Of course, running containers on macOS means running some form of VM, because containers are Linux, macOS is not Linux, so you need to somehow bridge the gap. But also, we wanted to use the excellent GPU we have on Apple Silicon devices, which means we need to somehow be able to access the GPU of the host from the VM. We already have built-IO GPU, which has some primitives to be able to implement transport and share memory between the host and the guests. But of course, macOS talks Metal, but our guest has no support of Metal whatsoever, and we don't expect to have support of Metal in anytime soon, or not soon even. So we need to somehow translate it. Luckily, there is this project from the Kronos group, which is called MoltenVK, which translates GL/HL shaders from Vulkan into Metal shaded languages. So you can then, they are then translated and provided to the Metal framework, so they are can be loaded on the GPU. So what we're doing here is by using the libkrun VMM and using krunkit, we are linking the VMM with MoltenVK, and we are enabling Mesa to talk on the VM to talk with MoltenVK through built-IO GPUs. And that allows us to run inferencing tools such as llama.cpp with the Vulkan backend all the way using the GPU on the host. I like to mention here that there are actually two backends on llama.cpp for Vulkan. One is called ggml compute, the other is called ggm Vulkan. Just ignore compute. It was interesting back in the day because it provided simple shaders, which potentially could have been better for simple GPUs like the one in Apple Silicon. But these days, the Vulkan, the ggml Vulkan backend has improved so much that the compute one doesn't make any sense. I even suggested to just remove it from the project. So to enable using RamaLama on macOS these days, it can be as simple as installing Podman desktop and creating a VM choosing the provider. libkrun has the provider. You can also, if you don't want to use Podman desktop, you can also just simply install Podman for macOS and configure manually the provider to be libkrun. In both cases, it will work the same way. Once you have this there, you can just rely on RamaLama as you will do on any other system. These are the old slides, and I think we can go directly to the demo. Back to Eric.
I'm just going to do a quick demo. I don't think the streamers are going to be able to see it, unfortunately, but at least people locally here at the event will see it, just to show how we put everything together on a real ARM device. Okay, so if I open up a couple of terminals, this is just going through what Sergio just described. So if I run RamaLama serve Gemma 3 on my MacBook here, this is starting an OpenAI compatible server in a container. So if I do podman-ps on the right, you'll see it started the RamaLama container running the server in the Gemma model essentially. And for this demo, I'm going to run a second container with pretty much the most popular UI for chatbots called OpenWeb UI. I'm going to run this script. It's just a big long podman command. Don't worry about the details too much. So if I execute that, now I'll open another terminal again. Now you'll see we have two containers running. Basically, one is running RamaLama and the inferencing workload, which is going to do the Vertio GPU stuff that Sergio just spoke about, and the other one's just running OpenWeb UI, which acts as the UI. So I'm going to run mvtop just to show you the GPU utilization. And if I go to my browser, so this is this OpenWeb UI I was speaking about. Okay, so I am at Linaro Connect. How do I get a huge round of applause? Audience on response of this query. Yeah, and you'll see the GPU graph there on the left. It's at like 96%. So that's basically a demo of what Sergio described there. So that's pretty much it. So thanks, everybody. And I don't know if we have time for Q&A.
Okay. Have you had a chance to do a comparison of how fast the models run on M4 Silicon with SME versus doing it the Vulkan way?
This is an M3. I personally don't own an M4, but maybe Sergio has. I don't know.
No, I don't think so. I don't think we haven't started testing performance yet, especially on M4.
Because I'd be interested to know.
Yeah, the main.
Oh, that was the other question. Was SME supported in the what runtime are you using there? Is it the ollama?
Is llama.cpp.
This is
like a great question for the chatbot.
Yeah, no, that's just so me and Sergio are contributors. That's just vanilla upstream llama.cpp.
Right.
This is running a backend which Sergio spoke about earlier. It's called compute in the code. We're actually migrating. There's 2 Vulkan implementations in llama.cpp, which is kind of strange, but we're actually moving to another implementation which is just called ggml Vulkan in the code. That's actually even faster than this one, to be honest.
So the reason to offload the workload to the GPU is not, well, you want to get good performance, but the real reason is to free up the CPUs for other tasks. Because we are thinking about this to be a development platform, so you are probably running multiple containers, you are building stuff, and you don't want your inferencing to take time from the GPU, from the CPU, so you want to get it.
I think his point about SME is good for things that unblocks in the future in terms of edge inference on a CPU without edge inference. I think it's an interesting thing too.
If anybody has any more questions, feel free to ask after, but we're out of time basically. Thanks everyone.